The information in this presentation applies to all MR systems, but the effects discussed are more relevant for MR systems with stronger gradient systems. Apart from the powerful static magnetic field and the RF field, each MR system applies switched gradient magnetic fields to define the position of structures within the human body. Unlike the static magnetic field, the RF and gradient fields are only active during scanning. However, in common with the static magnetic field and the RF field, the gradient magnetic field system requires certain safety precautions. This presentation begins with a short introduction of the system creating the dynamic gradient magnetic field. The next section describes the potential hazards of the gradient magnetic field and the way in which they can be prevented, followed by the consideration of possible contraindications. Finally, the presentation concludes with a summary and a list of the appropriate safety precautions. Gradient magnetic field introduction. Every MR system includes a carefully designed set of gradient coils. The gradient coils create the switched gradient magnetic fields needed to determine the location of the RF signal emitted by the protons in the human body. The gradient fields are applied in three orthogonal planes, the X, Y, Z planes, and are switched on and off only during scanning. The strength of the gradients is determined by the amplitude of the gradient magnetic field, measured in Tesla per meter, and by the switching time in seconds. It is therefore expressed in units of Tesla per meter per second, the slew rate of the gradient system. Higher amplitudes and shorter switching times result in a higher slew rate of the gradient magnetic field. The three independent gradient coils generate the gradient magnetic fields for each of the three orthogonal directions and are created by copper leads carefully positioned on the coil housing. The stray field of the gradient magnetic field outside the magnet bore is much smaller than that of the main magnet, but may not be neglected. Potential hazards. Although the switched gradient magnetic field is much weaker than the static magnetic field, the rapid changes in gradient field strength present two different effects that may result in a hazardous situation. These are acoustic noise and nerve stimulation. The acoustic noise results from mechanical forces on the gradient copper leads. These forces, known as Lorentz forces, are due to high electric currents applied through the copper leads, which lie within the static field of the main magnet. Since the copper leads are not free to move, the sudden application of force results in the typical knocking sound of the system. This sound becomes louder with higher currents, shorter switching times, and a higher static magnetic field. The amount of acoustic noise generated can approach the maximum noise level allowed, requiring appropriate precautions. The acoustic noise generated by the system is not only relevant for the patient, but can also affect the operator or other personnel present in the examination room during scanning. The nerve stimulation results from the electromagnetic fields generated in the human body by the switched electric currents in the copper leads of the gradient coil. This effect is observed in the kilohertz frequency range as opposed to the RF system, which produces electromagnetic fields in the megahertz range and results in heating of the human tissue. A mild form of peripheral nerve stimulation can be accepted. This nerve stimulation effect is generally only relevant for the patient. As a result of the stray field, the effect may become relevant for medical personnel, such as an interventionalist who approaches the patient during scanning. Preventing potential hazards. For acoustic noise, Exposure to a higher level than 140 dB peak noise is never allowed to prevent permanent damage to hearing. Temporary hearing damage can occur at lower noise levels. International MR safety standards for patients allow a maximum sound level of 99 dB/A for up to 1 hour. To keep the exposure below this level, some hearing protection in the form of earplugs or a headset is necessary and obligatory for almost all MR systems. Earplugs are not always effective for all patients. Positioning of the plugs in the ear is a tedious job. Headsets can also be applied incorrectly, and in the case of children and babies, this can become a practical problem. Peripheral nerve stimulation can become painful or even intolerable at the stronger gradients of modern MR systems. Therefore, International MR Safety Standard specifies limits for the allowed gradient output. From the literature, it is known that the threshold level for cardiac nerve stimulation is about a factor of 10 higher than that for peripheral nerve stimulation. Consequently, the occurrence of peripheral nerve stimulation provides a good warning and protection level for preventing cardiac stimulation. Peripheral nerve stimulation is first observed as a slight contraction of the skin. This can vary considerably in position over the body and is very subjective. There is no known long-term health effect related to the nerve stimulation. The gradient output level of every MR system is automatically limited to values of the mean threshold level for patients. However, since this threshold level is very subjective, sensitive patients may feel some peripheral nerve stimulation during routine scanning. Contraindications. Since all patients can usually be provided with hearing protection, there are no patients for whom an MR examination is contraindicated in view of the acoustic noise production. Extra care must be given to sedated patients because they cannot indicate that the hearing protection is not applied correctly. Similarly, extra care is needed for young children and babies. There is still an ongoing debate about scanning pregnant patients and potential hearing damage for the fetus. So far, there have been no reports of negative effects of the acoustic noise of MR systems on the fetus. There is no specific class of patients for which an MR examination is contraindicated because of the possible occurrence of peripheral nerve stimulation. Because peripheral nerve stimulation could come as a surprise for the patient, patients should be properly informed of this possibility to avoid restlessness during scanning. Philips MR scanners have 3 levels for the gradient output, related to the mean threshold level for peripheral nerve stimulation in patients. Below 60% of the mean threshold level, low, no peripheral nerve stimulation is to be expected. Up to 80%, moderate, peripheral nerve stimulation may occur. From 80% up to 100%, high, peripheral nerve stimulation is more likely to occur and in very exceptional cases can even be painful. Scanning at levels above 100% of the mean threshold level is not possible. Summary. The gradient magnetic fields in modern MR systems are becoming increasingly stronger. This may result in more acoustic noise produced by the scanner and also increases the possibility of peripheral nerve stimulation. To avoid harm to the patient, the following precautions must always be taken, particularly for MR systems with strong gradient systems and high static magnetic fields. Always apply hearing protection for the patient. Take extra care to avoid hearing damage when scanning sedated patients or young children. All personnel present in the examination room during scanning should wear hearing protection. The patient must be properly informed about the possibility of peripheral nerve stimulation. Medical personnel close to the patient should be aware that they may experience a mild form of peripheral nerve stimulation during scanning. This video highlights some of the basic guidelines for safe operation of an MR system. It does not give a comprehensive list of all possible hazards. In addition to this, you must read and understand the chapter on safety in the instructions for use of the MR system. If issues are not clear, please contact your local physicist or application specialist. Provided that the appropriate safety precautions are observed, MRI is an inherently safe modality providing images of outstanding clinical value. The information in this presentation applies to all MR systems, regardless of magnet field strength. MR uses a powerful magnet to create images of the interior of the body. Because the magnet is so powerful, certain precautions are needed. This video starts with a brief introduction to the magnetic field of MR systems. Then the potential hazards and the prevention of potential hazards are mentioned. Next, the contraindications that might pose a hazard to the patient are discussed, followed by the health aspects of static magnetic fields. The video concludes with a summary and a list of the appropriate safety precautions. Magnet Field Introduction. The magnetic field will attract objects made of steel or other ferromagnetic materials with enormous force. Even heavy objects can fly into the magnet. The magnetic field can also create torque forces on ferromagnetic objects, such as some implants, which may cause tissue damage. Although it cannot be seen or felt directly, the magnetic field of an MR system with a superconducting magnet is always on and must always be treated with respect. The main magnetic field generated by the magnet is not completely contained within the bore of the magnet. In fact, the magnetic field goes right to the edge of the room. All magnets are surrounded by a magnetic field, represented by the magnetic field lines. In a cylindrical system, the field lines are horizontal, but in an open system they are vertical. This means that the magnetic field around the magnet is different, creating different effects within the field. The limit of safety for ferromagnetic materials and magnetically sensitive devices, such as pacemakers, is known as the 5 Gauss line. For most sites, the 5 Gauss line lies just within the examination room. So it is advisable never to bring ferromagnetic objects into the examination room. Potential hazards. The magnetic field will pull ferromagnetic objects towards the magnet. In this way, a large metal object such as an oxygen tank or cleaning machine can become a missile. Small objects are pulled into the magnet at very high speeds, posing a significant risk. Even a spoon or coins can be dangerous. The magnetic field also twists ferromagnetic objects into line with the direction of the magnetic field lines. The twisting or torque forces can be dangerous in patients with ferromagnetic implants, because this force can displace the implant, tearing tissue or rupturing blood vessels. Brain aneurysm clips are particularly at risk from this effect. The magnetic force increases rapidly as you get closer to the system. If we hold an object a few meters from the magnet, we might feel little force, but closer to the magnet, the forces are substantially higher. This effect is even greater in the case of the actively shielded magnets. These forces are generally higher in the case of open systems, even when the magnetic field is lower than that of a cylindrical system, due to the different design of the magnet. Scanning a patient at field strengths above 2 Tesla represents a proportionately higher risk, requiring additional attention to the patient. The magnetic field can also affect the operation of magnetically sensitive active implants, such as pacemakers. And remember that the magnetic field can damage watches and erase magnetic data carriers, including credit cards. Preventing potential hazards. To keep your MR suite safe, follow these simple precautions. Post warning signs to alert everyone about to enter the restricted area of the MR suite. All personnel must know the location of the 5 Gauss line. Screen everyone who enters the MR suite and make sure they follow the MR safety guidelines for their own safety and the safety of others. Remember that these guidelines are not only for patients and medical staff, but also for cleaners, service engineers, medical and non-medical emergency personnel, including firefighters, and anyone else who might possibly enter the MR suite. Screen everyone for ferromagnetic objects in their bodies, such as implants, bullets, and shrapnel. And screen everyone for metal on or attached to their bodies, such as hairpins, brassieres, buttons, zippers, jewelry, and body piercings. Even makeup and tattoos can contain ferromagnetic material. Remove all makeup and be alert to the possibility of irritation in tattoos. Ensure that patients wear hospital gowns without metallic fasteners. Patients' ordinary clothing can contain magnetic objects or threads that may pose a hazard in the MR environment. Any equipment brought into the MR suite must be made of a non-ferromagnetic material and approved for use in an MR suite. The tools used by service engineers must also be made of special non-magnetic material. Note that equipment or tools which have been approved for use with magnets of up to 1.5 Tesla may no longer be suitable for use at 3 Tesla because of the higher forces at this field strength. Some common items that must never be taken into the MRI scan room include pulse oximeters, clipboards, stethoscopes, scissors, pagers, and pens. In an emergency, press the quench button. This will switch off the magnetic field within about 20 seconds. This must only be done in the case of a real emergency, when switching off the magnet is urgently needed. Bringing the magnet back on field is a very expensive and time-consuming procedure. Contraindications. Contraindications are conditions that might pose a hazard to the patient. They must be assessed by a qualified person prior to the examination. Ferromagnetic implants, such as aneurysm clips, and electronically active or passive implants, such as pacemakers and deep brain stimulators, are in principle contraindications for MR scanning. There is also a risk in scanning patients who may have embedded metal fragments in or near the eye. Machine tool operators, metal workers, and welders should be given an X-ray examination to detect the presence of any metal particles. Pregnant patients can be scanned when absolutely necessary. This is a matter of clinical judgment. If pregnant patients are scanned, they are scanned at magnetic fields of 1.5 Tesla or below, at reduced SAR levels, and not during the first 3 months of pregnancy. Health aspects. Since the introduction of MRI scanners in clinical practice in the mid-1980s, some 500 million patients have been scanned. Most of these examinations have been performed with 1.5 Tesla systems. No long-term negative health effects directly related to the static magnetic field have ever been reported. Summary. The magnetic fields around modern MR scanners are becoming increasingly stronger. Extra safety precautions are therefore essential and should never be forgotten. Remember the following points. The magnetic field around the magnet is always on. The magnetic force increases rapidly close to the scanner. All personnel must know the location of the 5 Gauss line. Never bring ferromagnetic objects within the 5 Gauss line area. All equipment in the MR suite must be certified as MR safe. Warning signs must be clearly posted. All persons must be screened before entering the MR suite. Have any contraindications assessed by an appropriately qualified person. Only use the quench button in a real emergency. This video highlights some of the basic guidelines for safe operation of an MR system. It does not give a comprehensive list of all possible hazards. In addition to this, you must read and understand the chapter on safety in the instructions for use of the MR system. If issues are not clear, please contact your local physicist or applications specialist. Provided that the appropriate safety precautions are observed, MRI is an inherently safe modality, producing images of outstanding clinical value. Philips Medical Systems has prepared a set of safety videos for education and training purposes. Apart from a short MRI introduction video, there are 3 separate safety video modules, which address RF safety aspects, magnetic field safety aspects, gradient magnetic field safety aspects. All the videos can be selected separately. Understanding the potential hazards of magnetic resonance imaging requires some knowledge of the basic principles. Living tissue contains a large amount of water, composed of hydrogen and oxygen atoms. Magnetic resonance imaging uses the nuclei of the hydrogen atoms, known as protons, to produce images. MRI can be used to show the position and concentration of the protons in the body, corresponding to the position of the various tissues as well as the tissue characteristics. Magnetic resonance imaging requires three main components: the magnet, the gradient coils, and the RF transmit and receive coils. The magnet creates a very strong magnetic field that aligns the protons in the body. The gradient coils change the magnetic field in three planes, so that the targeted protons have a different vibration frequency from their surroundings. This allows localization of the protons. The RF transmit coil broadcasts an RF signal at a given frequency, the resonance frequency. The targeted protons absorb the RF energy. These excited protons produce an RF signal which is picked up by the RF receive coil. The detected signal provides the data needed to create an image. Magnetic resonance imaging, or MRI, produces high-quality images of the body without using ionizing radiation. Nevertheless, the radio frequency used does require some safety precautions. Although modern scanners are designed to provide a high degree of safety, potential hazards still exist. This video starts with a brief introduction to RF and an explanation of the RF radiation effect. Next, the prevention of unwanted antennas is discussed. Then, the various types of RF effects are mentioned, together with the conditions under which they can occur. The video concludes with a summary and a list of the appropriate safety precautions. RF introduction. To be able to image protons in a large volume, it is important for the applied RF energy to be homogeneous over the whole region of interest. For this reason, a large RF transmit and receive coil, the RF body coil, is built into the scanner. The region of interest is placed in the center of the RF body coil. The closer an RF coil is to the patient, the stronger the detected signal will be. For this reason, small RF receive coils can be positioned close to the region of interest for detailed studies. Some examples are head coils, knee-foot coils, and multipurpose flexible coils. RF radiation effect. The transfer of energy to living tissue has a warming effect, similar to that created by a microwave oven, but much weaker. The patient may experience a feeling of warmth, but there are generally no side effects. Precautions are needed to avoid the occurrence of RF burns, such as local skin reddening or blisters. Unfortunately, apart from the receive coils, resonant induction loops can be created accidentally. These may act as additional unwanted RF antennas. Electronic RF filtering is applied to prevent cables and other components of RF receive coils becoming part of potential unwanted antennas. Unwanted antenna prevention. Cables should be positioned parallel to the main axis of the patient support. Loops must be avoided, and cables must not cross each other or other electrically conductive objects. There should be a layer of insulation between the patient and the coils. Philips systems are designed to ensure the optimum separation distance. But under some conditions, for example, if the patient's arms are within the scanner, extra padding may be needed. An unwanted antenna effect can also be caused by the interaction between cables or coils and the patient's body, or even between adjacent skin surfaces, particularly if the patient is sweating, as this increases the skin conductivity. Types of RF effects. International standards set limits to the level of applied RF energy, expressed as the specific absorption rate, or SAR. However, RF energy absorbed in unwanted antennas can lead to local SAR values exceeding these safety limits. This can lead to RF burns in several different ways. A cable or component in contact with the patient's skin can heat up and cause a burn. Currents running below the skin can cause internal burns. In this case, the component is not heated. In the case of skin-to-skin contact, the surface area is small so that high-energy discharges can occur. Conditions. The likelihood of an incident increases with the RF energy level. Since high-field systems operate at higher RF energy levels, particular attention must be paid when using high-field systems. Over the course of time, RF coils are subject to wear and tear. Never use damaged RF coils. There is a growing tendency to scan with SAR levels approaching the maximum of 4 watts per kilogram for a whole body scan. This can warm up the patient, resulting in increased perspiration. It is advisable to minimize the use of scans with high SAR levels. Shorter image reconstruction times result in shorter intervals between the scans, so the patient has less chance to cool down. It is therefore advisable to spread the high SAR scans across the entire exam by interleaving them with lower SAR scans. Summary. Although MRI is an inherently safe diagnostic modality, provided that the appropriate safety precautions are observed, there are still some potential hazards, including the possibility of RF burns. Modern scanners have built-in safety features that are designed to prevent this problem. However, as more and more electronic devices are added to the patient, careful positioning becomes increasingly important. Some safety precautions should always be observed. Remember that RF coils may heat up during scanning. Minimize the use of high or default SAR mode. Schedule patient cool-down breaks between high SAR scans. Prevent skin-to-skin contacts, creating current loops. Keep sufficient distance between RF coil cables and the patient's skin. Keep RF coil cables straight, avoid loops. Keep RF coil cables parallel to the main magnetic field. Keep RF coil cables and ECG/VCG cables separated. When combining RF coils, pay special attention to cable handling. Never use damaged coils. This video highlights some of the basic guidelines for safe operation of an MR system. In addition to this, you should read and understand the chapter on safety in the instructions for use of the MR system. If issues are not clear, please contact your local physicist or applications specialist. Provided that the appropriate safety precautions are observed, MRI is an inherently safe modality producing images of outstanding clinical value.